Hello and welcome. Today we are going to explore the concept of permutations. You might have seen this mathematical notation before, the letter N followed by a capital P followed by the letter R. If you've ever felt confused by this, you are in the right place. This is a tutorial designed for absolute beginners. We will take it step by step, nice and slow, so you can truly understand what this means. Let us start by looking at our roadmap for this lesson. We have 8 simple steps to guide us. First, we will answer a basic question: what is a set? Then, we will define exactly what a permutation is. After that, we'll draw some visual diagrams. We'll look at a 2-level tree where we pick 2 items from 3, a 3-level tree where we pick 3 from 3, and a slightly wider tree where we pick 2 from 4. These visual trees will naturally lead us to something called the slot principle. From there, we'll look at a special case known as n factorial, written as n with an exclamation mark. Finally, step 8 will bring everything together, and we will actually derive the permutation formula ourselves. On the right side of your screen, you can see this final formula for nPr. It involves factorials, an n and an n minus r in parentheses. Right now, it might look a bit intimidating, but do not worry at all. By the end of this journey, you will know exactly where every single piece of this formula comes from. Let us begin at the very beginning with step 1, the starting point. Before we can arrange things, we need things to arrange. In mathematics, we call this a set. By definition, a set is simply a collection of distinct objects. Distinct just means that every object is completely unique. There are no exact duplicates. Let's look at the set notation in the middle of the screen. We use a capital letter S to represent our set. Then we have an equal sign followed by curly braces. Inside those curly braces, we list our objects, A, B, C, and D. On the right side of the screen, you can see a visual representation of this. The large blue oval represents our set S, and inside it we have 4 distinct elements, each sitting inside its own orange circle, A, B, C, and D. Let's count them. 1, 2, 3, 4. Because there are 4 items in total, we say that our total count, represented by the lowercase letter n, is equal to 4. So each circle is 1 element, and n represents the total number of elements in our set. Now that we know what a set is, let's move to step 2 and ask, what is a permutation? The simplest definition is right there in the green box. A permutation is an ordered arrangement of objects. The most important phrase here is ordered arrangement. Let's look at an example. Suppose we have a new, slightly smaller set, S, which contains just 3 letters, A, B, and C. Now, imagine we want to pick exactly 2 of these letters, one after the other, to form a sequence. Let's see all the possible ways we can do this. We could pick A first, then B, giving us AB, or we could pick A then C, giving us AC. If we start with B, we could get BA or BC. And if we start with C, we can get CA or CB. Over on the right, inside the yellow box, is the golden rule of permutations. Order matters. If you look at the pair AB and the pair BA, they contain the exact same letters, but because the sequence is different, because A is first in one and B is first in the other, they are not equal. AB does not equal BA. In the world of permutations, these count as 2 completely different arrangements. Now let's visualize this process of picking objects by building what we call a tree diagram. This is step 3. We're using our set of 3 letters, A, B, and C, and we're going to pick exactly 2 of them. We begin at the very top, at the dark green circle labeled Start. At this point, we haven't picked anything yet. Now we make our first pick. Looking at the arrows pointing down from Start, we can see 3 possible paths. We can choose A, we can choose B, or we can choose C. This is our first level of the tree, And as you can see at the bottom of the screen, for level 1, we have exactly 3 choices. Let's imagine we walked down the first path and chose the blue circle A. Now we need to make our second pick to complete our pair. Since we have already used A, only B and C are left in our set. So from the circle A, the tree branches out into 2 paths, one leading down to B, giving us the final pair AB in the green box, and one leading down to C, giving us the final pair AC. The exact same logic applies to the other branches. If we chose the green circle B first, we're left with A and C for our second pick, giving us BA and BC. And if we chose the red circle C first, we're left with A and B, giving us CA and CB. Notice that for every single choice we made in level 1, we always had exactly 2 choices remaining for level 2. So, how many final arrangements do we have at the very bottom of the tree? We have 3 initial branches, and each of those splits into 2 smaller branches. By multiplying our choices, 3 times 2, we get our total number of arrangements, which is 6. You can count the dark green rectangles at the bottom to verify. There are exactly 6 unique pairs. Now, let's expand our view and move to step 4. We're going to look at a 3-level tree. We still have the same set of 3 letters, A, B, and C. But this time, instead of just picking 2, we're going to pick all 3 of them in order. We start at the top, just like before. For our first pick, level 1, we have the whole set available. We can choose A, B, or C. That gives us 3 choices. Let's follow the leftmost path again. We pick A. Now, for level 2, we have 2 choices remaining, B or C. Let's say we pick B. At this point, we have chosen A and then B. Now we must make our third and final pick for level 3. But look at our set. We have already used A and we have already used B. There's only one letter left in the entire set, and that is C. So from the letter B, there is only one straight downward arrow pointing to C. We have no other options. This gives us our final 3-letter arrangement in the green box at the bottom, A, B, C. This pattern holds true across the entire tree. By the time you reach the 3rd level, there's only one choice left for every single path, completing sequences like ACB, BAC, BCA, CAB, and CBA. Let's look at the math at the bottom of the screen. For level 1, we had 3 choices. For level 2, we had 2 choices. And for level 3, we had exactly 1 choice. To find the total number of arrangements, we multiply these choices together. 3 times 2 times 1. 3 times 2 is 6, and 6 times 1 is still 6. So there are a total of 6 ways to arrange all 3 letters. In mathematics, when we multiply a sequence of descending whole numbers all the way down to 1, like 3 times 2 times 1, we use a special shorthand. We write it as the number 3 followed by an exclamation mark, and we read it out loud as 3 factorial.
Now, let us take a moment to look back at the 3-level tree we just built and carefully read what it is telling us. At the very top, we have the root, which is our start point. Here, we have made no choices yet. Then we move to level 1, which you can also think of as slot 1. Because we are just starting, we have all 3 choices available to us. Once we make that first pick, we move down to level 2, or slot 2. Because one item is already gone, we now have only 2 choices left. Finally, we reach level 3, or slot 3. 2 items are gone, leaving us with exactly 1 choice. If you look at the purple box on the right, you will see the math for this. 3 times 2 times 1 equals 6. And as we learned, this is equal to 3 factorial. In general terms, that is n factorial. The most important takeaway is written in the orange box at the bottom. Each level uses up 1 element. Therefore, our choices shrink from 3 down to 2 down to 1. Let us try another visual example to make sure we really understand this. This time, we are going to look at a wide tree. Our set is slightly larger now. It contains 4 elements, A, B, C, and D. Our task is to pick exactly 2 of them. Once again, we begin at the dark green start circle at the top. For our very first pick, we have 4 options. We can travel down the branch to the blue circle A, the green circle B, the red circle C, or the purple circle D. Let us imagine we picked the blue A. Now we need to make our second pick. Since A is used, we have exactly 3 letters left, B, C, and D. So from A, we have 3 smaller branches leading to our final pairs, AB, AC, AD. This exact same pattern happens no matter which letter we choose first. Every single one of our 4 initial branches splits into 3 smaller branches. At the bottom of the screen, we can calculate the total simply by multiplying. We have 4 branches times 3 leaves each, which equals 12 total arrangements. On the bottom right, we see a new piece of notation to describe what we just did. We write a small 4, a capital P, and a small 2. We read this as 4 permute 2, and as our tree shows, it is equal to exactly 12. Now that we have drawn a few trees, we can start to see a clear pattern emerging from them. Let us look at the boxes on the screen to summarize what we have learned. In the top blue box, we have our first example. From a set of 3, we pick 2. The math is 3 times 2, giving us 6 arrangements. In the red box below that, we have our second example. From a set of 3, we pick all 3. The math is 3 times 2 times 1, which also gives us 6 arrangements. In the purple box, we have our wide tree example. From a set of 4, we pick exactly 2. The math is 4 times 3, giving us 12 arrangements. Do you see the pattern? It is written in the orange box at the bottom. Every time an element is chosen, 1 fewer choice remains for the next pick. You start with your total number of items, and you just multiply by 1 number lower for each step you take. This beautiful, simple pattern leads us directly to a very important concept called the slot principle. Imagine you are filling a series of empty boxes or slots from left to right. Let us look at the diagram. For slot 1, you haven't used any objects yet, so you have all n objects available to choose from. For slot 2, you have used up 1 object, so your choices shrink to n-1. For slot 3, you have used up 2 objects, so your choices shrink again to n-2. This pattern continues, indicated by the 3 little dots in the pink box. You keep multiplying until you reach your very last slot, which is slot R. At this final position, the number of choices you have left is n minus r plus 1. Notice the long red arrow underneath, reminding us that there are exactly r slots to fill. By multiplying all these slot choices together, we get the mathematical formula for a permutation. It is written in the purple box at the bottom. nPr equals n times n minus 1 times n minus 2, and so on, all the way down to n minus r plus 1. Let us ground that abstract formula with a really simple, concrete example. We'll use the slot principle with n equal to 3 and r equal to 2. This means we have 3 objects in total, and we want to fill exactly 2 slots. Look at the visual equation on the screen. The blue box represents slot 1. Since we have 3 objects, we put the number 3 in that box. Then we multiply that by the pink box, which represents slot 2. Because we used 1 object in the first slot, we only have 2 choices left, so we put the number 2 in that box. 3 times 2 equals our green total box, which is 6. If you look at the lower left green box, it spells this logic clearly. Slot 1, pick from 3 objects, which gives us 3 ways. Slot 2, 1 is used, 2 remain, which gives us 2 ways. And just to prove that this math works perfectly, the box on the bottom right lists all 6 of those actual arrangements: AB, AC, BA, BC, CA, and finally CB. Now, let us take a closer look at a special case we mentioned earlier, n factorial. This happens when we want to arrange all of the elements in our set.
The key idea is clearly stated at the top of the screen. When we arrange all n elements, we are setting our chosen number r to be exactly equal to our total number n. This specific count is called n factorial, and it is written as the letter n followed by an exclamation point. The formula is shown in the red box right below. N factorial equals n times n minus 1 times n minus 2 and so on, shrinking by 1 each time until you multiply by 2 and finally multiply by 1. Let us look at the example at the bottom. We have our familiar set of A, B, and C, and we want to arrange all three of them. Following our rule, 3 factorial equals 3 times 2 times 1, which gives us 6. And over on the right, inside the red bordered box, we can see those 6 arrangements completely spelled out for us. ABC, ACB, BAC, BCA, CAB, and finally CBA.
Let us explore a fascinating connection. As we can see on this slide, titled n factorial is a special case of nPr, we are looking at what happens when we decide to arrange all of the objects we have. If we set the letter r, which is the number of objects we are choosing, equal to the letter n, which is our total number of objects, our permutation formula becomes nPn. This means we are finding the number of permutations of n objects taken n at a time. This is equal to n multiplied by n minus 1, continuing all the way down to 1. And as we learned earlier, this is the exact definition of n factorial, written with an exclamation mark. To help you get comfortable with these numbers, let's look at the blue table on the left, showing n on one side and n factorial on the other. If n is 1, 1 factorial is simply 1. If n is 2, 2 factorial is 2 times 1, which is 2. If n is 3, 3 factorial is 3 times 2 times 1, which equals 6. If n is 4, 4 factorial is 4 times 3 times 2 times 1, giving us 24. And if n is 5, 5 factorial is 5 times 4 times 3 times 2 times 1, which equals 120. Notice how quickly the numbers grow. Over on the right, inside the green box, we have a clear definition to remember. n factorial counts all the possible ways to completely rearrange n distinct objects. Therefore, nPn is simply equal to n factorial. Now we arrive at a very exciting part, deriving the actual mathematical formula. Step 1 is to spot the pattern. In the top teal box, we have our slot principle written out mathematically. nPr is equal to n times n minus 1, continuing all the way to the last slot, which is n minus r plus 1. Now look at the red box directly below it. Let us write out the full expansion for n factorial. n factorial is equal to n times n minus 1, continuing all the way down to n minus r plus 1. But because it is a full factorial, it doesn't stop there. It keeps multiplying. It multiplies by the next number down, which is n minus r, then n minus r minus 1, all the way down to the number 1. Look closely at the black curly brackets underneath this long equation. The key insight is written at the bottom of the screen. n factorial actually contains nPr as its leading block. The first half of that long multiplication, everything up to n minus r plus 1, is exactly nPr. The second half of that multiplication, starting from n minus r and going down to 1, is exactly the factorial of n minus r. So let's put this discovery together on the next screen. Step 2 is to isolate our permutation. In the top blue box, we start with the equation we just discovered from our pattern. nPr multiplied by n minus r factorial is exactly equal to n factorial. But we want a formula just for nPr all by itself.
Using basic algebra, we can divide both sides of this equation by the term n minus r factorial. When we do that, we get the beautiful result shown in the purple box in the middle of the screen. nPr is equal to n factorial divided by, in parentheses, n minus r factorial. As the green box at the bottom proudly states, this is the famous permutation formula. You don't have to draw huge trees anymore. You can simply plug your numbers into this elegant equation. But does this new formula actually work? Let us verify that the formula matches the trees we drew earlier in the lesson. In the top blue box, let's calculate 3p2. Our total n is 3, and we are choosing 2. Using our formula, this is 3 factorial divided by the factorial of 3 minus 2. 3 minus 2 is 1, so we have 3 factorial divided by 1 factorial. That is 6 divided by 1, which equals 6. If we check the green text on the right, we see a check mark. Yes, our two-level tree from earlier had exactly 6 leaves. Next, in the middle red box, let's calculate 3p3. We are choosing all 3 items. The formula gives us 3 factorial divided by the factorial of 3 minus 3. 3 minus 3 is 0, so we have 3 factorial divided by 0 factorial. Now, please look down at the orange box at the bottom of the screen. There is a very important rule in mathematics. 0 factorial is equal to 1 by definition. Don't let it confuse you, it just equals 1. So back to our red box, 6 divided by 1 equals 6. There's a check mark confirming that our 3-level tree also had exactly 6 leaves. Finally, in the purple box, let's try a larger set, 4p2, choosing 2 items from a set of 4. Our formula is 4 factorial divided by the factorial of 4 minus 2. This becomes 4 factorial divided by 2 factorial. 4 factorial is 24, 2 factorial is 2. 24 divided by 2 gives us 12, and the check mark confirms that our wide tree from earlier had exactly 12 leaves. The formula works perfectly. Here's a quick reference guide to help you easily recall all the symbols and terms we have used. The lowercase letter n represents the total number of objects in your set. The lowercase letter r represents how many of those objects we are choosing. The symbol nPr represents the final permutation or arrangement count. The letter n followed by an exclamation mark is read as factorial of n. The word slot refers to one specific position in the arrangement we are building. And the letters A, B, and C, and so on, represent the individual elements, which were the orange letters sitting on the tree edges in our earlier diagrams. Let us bring everything together with a summary of the complete picture, tracing our journey from the very beginning. We always start with a set of n distinct objects. From that set, we choose r of them to fill r-ordered slots. To find the total number of ways to do this, we use our slot counts, starting with n, then n minus 1, continuing down to n minus r plus 1, and we multiply them all together. We also learned about a special case. When r equals n, meaning we arrange everything, the product simply becomes n factorial. And all of this logic flows downward to give us our master equation, sitting at the bottom of the screen in the purple box. nPr is equal to n factorial divided by, in parentheses, n minus r factorial. As the green box at the bottom proudly states, this is the famous permutation formula. You don't have to draw huge trees anymore. You can simply plug your numbers into this elegant equation. Please consider liking, sharing, and subscribing to join our gentle community, and I would truly love to hear your wonderful thoughts in the comments below.